Hello and welcome to this new series of videos I'm going to be making. So these are all based on the Edexcel GCSE Physics Specification. So in each video I will try and highlight which of the two papers the content I'm delivering is relevant to, and I will also try and differentiate between which tier, either foundation or higher, it's in as well. So we're going to start off with section 1 from the specification. So these sections are all named after what they are in the actual specification made by PSN Edexcel. So we're going to start off with topic 1, key concepts in physics. This is the only topic which is in both of the exam papers, because it's just some very fundamental skills that get used throughout all areas of physics. So let's get stuck in. So everything I'm going to do in this video is included in both foundation and higher tiers. So there's not going to be any differentiation between the two in this video, but for most of the other videos there will be. So let's start off with part 1 of section 1, looking at recalling the SI unit for physical quantities. So let's just dig into a few things here that it's worth knowing about. So first of all, what do we mean by this term here, physical quantities? Well, basically what we mean is it's something. I'm getting used to using this handwriting tool, so it might be a little bit messy to start with. You can measure. Okay, so that's what makes something a physical quantity. So there are 7 what we call base quantities. So these are quantities that between the 7 of them you can measure any quantity you might be interested in. So you'll notice on here there is a list of 6. The 7th one we, to be honest, don't really use unless you're in a very specific area of physics. So that's the unit of light intensity, or the candela. But these are the 6 that we will be coming across as we go through the course. So if we take a look at them, we've got our first quantity, which is the quantity for distance. And its standard unit is the meter, unless you're over in America, in which case they use yards, but we're not in America, so we won't. So we measure that in meters. We don't usually write meters, we just write M for short. Next, we've got our unit for mass, which is the kilogram. This is where physics goes in a slightly different direction to chemistry. So in chemistry you'll pretty much work in grams the whole time. In physics the SI unit is the kilogram. Eventually chemistry does get on board and they just start using kilograms as well, but you might notice a bit of difference at this stage. We don't write kilograms out all the time, we're going to write kilogram or kg. Next we've got our unit for time. And our standard unit for time is the second. We can measure in lots of units like hours, minutes, days, but our standard unit, the one that we use in equations, is the second. We don't write that out, we just write S for short. Once we get into electricity, we're going to be measuring electrical current, or the number of charged particles per second going through a point. We'll meet that quite a bit later on, but it is one of the base units. Its unit in full name is ampere. We usually, to be honest, just call it amps for short. Even more abbreviated, we just write a capital A in there. And it does need to be capitalized. So far they've all been lowercase, but this is a capital letter. Our 5th base unit is a unit for temperature. And you may not have actually come across this one. So in the UK we tend to use degrees Celsius for temperatures. If you're in America you use Fahrenheit, but in equations in physics we use a unit called Kelvin, and we'll learn more about that in a later topic. The final one that we actually don't really use at this level in physics very much is the unit of quantity, or just measuring how many of something you have, so maybe how many atoms you have, or something like that. You'll actually use this a lot more in chemistry at this level. Once we get to sixth form physics, we start using moles more there. And you'll see we really highly abbreviate it by removing one letter when we're writing this in here. So in terms of what these will look like, if we're giving a distance, we might measure 1 meter, we might measure, I don't know, 2.5 kilograms, we might have 0.5 seconds. So this is what it's going to look like when we're doing them. Remember, our ampere needs to be capitalized, as does Kelvin, incidentally. That is a capital K, so we're probably not going to get temperatures of 0.5 Kelvin, but it doesn't matter for now. And I don't know, maybe we have 2.1 moles. So this is what it will look like when you're writing answers to questions. We have a value and its unit. And we've met 6 of them, and just for completion, there is one more. So the other one is as I said, we don't come across it very much. It's for measuring, I'm pretty sure this is right. I barely use this at all in physics, to be honest. I believe it's a unit for light intensity or something along those lines. And I'm pretty sure it's CD for short, but I'm not entirely sure, mainly because I basically never used it. So those are our 7 base units. And there are more units than this, but those ones are called derived units because they are derived from these base units. So speed, we might measure in meters per second. You can see we've already got meters, we've already got seconds, so that's a derived unit. So let's actually get into that, because as we go through the course, we are going to meet some further units. So these can all be written in terms of base units, but we don't tend to because it would take a long time. So these are essentially abbreviations. So when we're studying waves, but also occasionally in some other topics, we'll come across a frequency. And in equations, you'll see that as the symbol F, lowercase f. And we measure that in a unit called Hertz. This is named after a famous physicist. I think a lot to do with the discovery of X-rays, if I remember correctly, but we don't tend to write out Hertz. We would write this in here, so maybe something has a frequency of 2000 Hertz, so it looks something like this. Forces we're going to come across quite a lot. Their unit is named after a very famous physicist, Isaac Newton, and we just write a capital N. Energy we measure in joules, who is a fairly well, at least in a physics sense anyway, he's a fairly well-known engineer, inventor of some of the first engines. We don't usually write joule, we just write a capital J. Power, again, the watt, again named after a reasonably famous engineer, at least in the physics world, he's famous. We just write a capital W. It does inspire a fairly terrible physics, I think joke is too strong a word for this, but essentially the way it will go is a student will ask me, what is the unit of power? And I will respond to them, yes. And they will get annoyed because they're like, no, what is the unit of power? And I'll go, yes, because what is the unit of power? So that's just me being annoying, but there we go. Pressure, again named after a fairly famous French scientist, Pascal. That's capital P, lowercase a. Charge, which we'll encounter when we get into electricity, is measured in coulombs, again named after a famous physicist, given the letter capital C. Potential difference, we'll also come across EMF. Also, they're all measured in volts, named after Alessandro Volta, who I think is an Italian physicist, capital V. Resistance is ohms, named after a German physicist, which is a Greek letter omega, that's a capital omega. And then once we get into magnetism, we'll come across magnetic flux density. That has a unit of Tesla, not named after the car company, named after the actual physicist Tesla, given a capital T. And so you'll come across these as you go through each of the different topics. So just to give you what their symbol is, so this is why it's important to differentiate between lowercase and capitals, because you can see the letters get used in both. So force is a capital F, energy is an E, capital E, power is a capital P, pressure is a lowercase p, so you have to be careful to differentiate between the two. Charge is given this symbol Q. Potential difference is usually given the symbol V. and you can see its units is also V, so some ripe for some confusion there. Resistance is measured in, or not measured in, it has a symbol R, so that's what you'd see in an equation. And magnetic flux density, in a really logical fashion, has the symbol capital B, which at this stage doesn't really make a whole lot of sense. So these are the symbols for them, and these are the units down here. Okay, so what we're going to do now is we're going to have a first of our kind of assessment checkpoints. So as we go through this video, obviously we're trying to learn some new material, and what I'll do is I will put in these checkpoints so you can see how well you've picked up some of the stuff we're trying to learn. I will put links to some documents in the description, and so the document is essentially just these assessment questions. It might be worth having a go at these before you start any of the videos, just to see if the video is actually going to be worthwhile watching. So there'll be a link to this, there's a Word one, and there's also a PDF in the description. So first challenge for you is list all of the base units. The seventh one I'm not too fussed about, but the other 6 you need to know. So I want to know, what are the other 5 quantities? What are they measured in, their full name, and what are their symbols? So pause the video and have a go at that now. Alright, so I'm going to assume that you have now had a crack. So let's see if I can remember these. So we've got time. The order of these is not important, so we've got time, mass. I'm just going to write temp. So temperature, we have quantity, we had current, and we also, I'm going to put this in brackets because we don't really need to know about this. We had light intensity. So the units of them, so we had the time, if it's in an equation, you can measure in seconds. Mass is a bit strange, it's measured in kilograms. Temperature is measured in Kelvin. Quantity is measured in moles. Current is measured in, I started writing C then, what am I doing? Amperes, or we usually call them amps for short. And light intensity are measured in candela. So you've got S, kg, capital K Kelvin, mole without the E, capital A, and I think it's just 2 lowercase letters CD, but I'm not entirely sure about the light intensity one. Alright, so that's the first of our assessment points. Depending on how you did with that, it might be worth having another crack at that later on. So if you only got maybe 3 of them, it's well worth coming back to and seeing if you remember them later on. This kind of task is something you should repeat frequently over time. Let's put another one in here as well. So we also met some derived units, so things that come from base units. So again, pause the video, see if you can write the symbol, the thing that you'd see in an equation, the unit for it, and what the unit symbol is. Alright, so I'm going to assume you paused the video and had a crack at that. So let's fill in all the symbols. So frequency is a lowercase f. Most of these are fairly logical, but you do have to remember if they're upper or lowercase. Force is capital F. Energy is capital E. Power is capital P. Pressure is a lowercase p. Charge, its symbol is Q. A lot of people will tend to put C for that, but it's Q. Potential difference, the symbol is V. Resistance, the symbol is R. And flux density, weirdly enough, the symbol is B. So the unit for frequency is hertz. The unit for force is newtons, or capital N, usually we write. Energy we measure in joules. There are other units for energy, like calories, kilowatt hours, and stuff like that. But the SI one is joule. Power we can measure in watts. You also do come across things like horsepower and stuff like that, but we measure in watts. Pressure we measure in pascals, which we write, strictly speaking, the capital P, lowercase a. Charge we measure, electrical charge we measure in a unit. It's a rather obscure name. We measure it in coulombs, capital C. Potential difference we measure in a volt. Resistance we measure in ohms, which is the only one of them that has a Greek letter, the capital omega. Flux density we measure in Tesla, again, not the company, the physicist Nikola Tesla. Okay, so those are our SI and derived units. Let's move on to the next part. So we're going to recall and use multiples and sub-multiples of units. So basically what that means is we're going to start using prefixes. And you will see these quite a lot with calculations, especially when you're dealing with really big numbers and really small numbers. So with prefixes, the key things to know is be able to recognize the symbol when you see them next to the unit, and then basically know what to do if you see that prefix. So this will just form one stage of a calculation. You'll need to spot the prefix and you'll need to know what to do with that prefix. And this will link in quite heavily with standard form, which we'll get to in part 4 of the last stage of this video. So we'll spend more time looking at standard form a bit later on. So these are the prefixes you'll come across in the GCSE course. There are quite a lot more than this. Those of you who do computer science will come across tera, which is the next one up from giga, and like exo and stuff like that. There are ones smaller than nano as well. I think pico is the next one, and then femto after that. So this isn't a complete list, but these are the ones you're going to be expected to know for GCSE level. So let's actually get into some examples so we can see what they are in action. So we can see in this one here, this first example, you can see there's this capital G. So if G tells us we need to multiply that number by 1 billion if we see it in a calculation, or in standard form, times it by 10 to the 9. So let's see what that looks like. So if we want to express it in meters, essentially what we're going to do is we're going to do 2.4, and we're going to now multiply it by 1 billion. Now 1 billion is 1 followed by 9 zeros, so we're going to end up with all of these zeros in here. Now writing out all these numbers is absolutely tedious, so as scientists we don't tend to do that. We would write that as 2.4 times 10 to the power of 9 meters. And what that means is it's 2 followed by essentially 9 places after it there. So this is what we call a decimal number. This in here is what we call a standard form number. And with really big numbers and really small numbers, we tend to use standard form. It's just much easier to work with. So you can see giga always means 10 to the power of 9. Let's have a look at a small one as well. So express 6.8. So you can see we've got a prefix here. It's always to the left of the unit. This is nanometers. So what we're going to do is we're going to do 6.8, and we're going to divide that by, oh boy, why did I pick the billions ones? Okay, so here we go. Okay, and there we go. This is the decimal form. We wouldn't usually write that. We would write 6.8 times 10 to the minus 9 meters. We'll have a look in a later section how you can convert between decimals and standard form, but I'll leave it as that for now. The key thing to pick up at this stage is be on the lookout for these prefixes to the left of units and know what the prefix tells you to do to the number in your calculation. That's the key thing at this stage. So let's take another assessment point in here. So what I've given you is the same table as above, but with some gaps in it to see if you can fill those gaps in. And then if you can do that, then also a couple of practice questions, including this more challenging one at the end, just to be a bit more interesting. So pause the video, have a crack at both these sections now. This one, the first section, and then this, the second part in there, and then we'll go through all of those. Okay, so let's start off by filling in the gaps in our table in here. So giga is a capital G in there. We've got all of those. This little c stands for centi, like in centimeters. When you see a K or a kilo, that tells you to multiply by 1,000. So 1 kilometer is 1,000 meters. Milli tells you to divide by 1,000. So if I have a distance in millimeters, I would need to divide it by 1,000 to turn it into meters. That's what that means. Micro, divide by million. Nano, divide by 1 billion. So you can see as we go each of these lines, they're each 1,000 times bigger, essentially. So a million in standard form is times 10 to the 6. Micro is times 10 to the minus 6 in there. This is actually the Greek letter mu, by the way. You can see most of these are the normal Roman alphabet, but this one is actually a Greek letter mu that's cropped in. You'll see Greek letters popping into science quite a bit as you go through. Let's have a look at these examples. So we want to convert 6.3, and the prefix in here is a kilo. So that means we are going to be timesing by 1,000. So you can see that that would be 6,300 meters. We could also write that as 6.3 times 10 to the 3 meters. That's the decimal. This is the standard form. This one we can see has got a milli, so that's not meters, it's to the left of a unit, so that's a prefix. So that's 1.4, and it's telling us to divide by 1,000. So that's going to be 0.0014 when we type that into our calculator, or we could write that as 1.4 times 10 to the minus 3 seconds. One final more challenging one, converting giga into kilometers. So this standard form is 10 to the 9. This is 10 to the 3. So what we're going to do to get between the two, we are going to times by 10 to the 6. So basically this is going to be 8.2 times 10 to the power of 6 kilometers. So that's in there, because a gigameter is a million times bigger than a kilometer, essentially. That's the logic that I'm using to try and figure that out. Don't worry too much if I've just completely lost you with this one. It's more important that you can do these first two at this stage. That one I just chucked in for a bit more interest. Okay, so we're over the halfway mark, on to part 3 of the 4 that we're going to cover. This is going to focus on converting between different units. So one quantity can have lots of ways of measuring it. So for example, distance we could measure in meters, we could measure in yards, we can measure it in light years, parsecs. There's loads of different units of distance, and we essentially need to learn how to convert between different things. The example that I've picked and that the exam board really emphasizes is converting between different times, which we'll come across a lot in different sections. So I've just picked out 4 that we're going to learn to convert into seconds, but the principles of converting are the same regardless of what the unit is. So these are the things you have to know. So you have to know that 1 minute is 60 seconds and that 1 hour is 60 minutes. You need to know that 1 day is 24 hours, and you need to know that a year is 365 days approximately. That's not quite right, but it's about right. So those are the things you need to know, and then essentially we use those to convert into seconds. So 1 minute is 60 seconds, so that one's nice and easy. That's just a fact you need to know. 1 hour is 60 minutes, and each minute is 60 seconds. So that means that 1 hour is 3,600 seconds, and we got that number by multiplying 60 by 60. 1 day is 24 hours. Each hour is 60 minutes, each minute is 60 seconds, so that's where this number comes from in here. We've done 24 hours times 60 minutes times 60 seconds there. And a year, it's a fairly hefty number in seconds, as you can see. There are 365 days in a year, 24 hours in each day, 60 minutes in an hour, 60 seconds in each minute, and that's where this number comes from. So it's not so important to learn these numbers, it's where they come from that's the important thing to take away here. So let's have a look at some examples before you have a go at some by yourself. So we want to convert 2 hours and 30 minutes into seconds. Now the first thing we need to do is express this as a decimal. So 30 minutes is half an hour. So this is 2.5 hours. And if we go to our table, we need to multiply it by 60 and then by 60 again. Which off the top of my head I have no idea what that is, so let's just quickly Google that. So 2.5 times by 60 times by 60. This is where my internet fails, which would be fairly annoying. There we go. That took a lot longer than I was. So we've got 9,000 in there, which sounds very plausible. So let's stick that in. Okay, 9,000 seconds. Let's have a go at a second example. So we want to do 6.5 days. So to turn it into hours, we would times it by 24. To turn it into minutes, we times it by 60. To turn it into seconds, we times it by 60. So let's do that. So 6.5 times 24 times 60 times by 60. And we have an incredibly slow search because you see my Wi-Fi is not awfully good in this cave that I'm hiding in to record this video. Hopefully we'll get there in a not terribly long period of time. Well, this is tedious, isn't it? Alright, this is handy. I'm sitting here with a phone, so let's just whip that out and do the calculation on there. 6.5 times 20 times 60. 60 times by 60 gives me, quite a long number. So I've got 561. 600 seconds in there. I'll stick to using my phone as calculator from now on, I think. Right, so those are some examples. Here are a few for you to have a crack at by yourself, again including a challenging one at the end if you want to look into this in a bit more depth. So pause the video, have a crack at that now. Alright, so I'm going to assume you've had a crack. So to turn days into seconds, we first turn it into hours, then we turn it into minutes, then we turn it into seconds. So let's just pop that into the old calculator. So 7.5 times 24 times by 60 times by 60, and that comes out as some very long number. That's a very large number of seconds, which shouldn't be too surprising. There we go. Then we've got 3 hours and 45 minutes. So this is 3 3/4 an hour. So 45 minutes is 3/4 of 1 hour. And so that's where this 0.75 has come from. So times by 60 turns it into minutes. Times by 60 turns it into seconds. So let's pop that into the calculator. 3.75 times 60 times by 60 gives us a still reasonably large number of seconds, but then it's quite a few hours, so that makes sense. So last part, don't worry too much if you have no idea what to do with this. So a year, the most precise figure I know for a year is actually 365.24 days. Quite often you'll see it rounded to 0.25, but it's actually I think 0.24. So our conversion factor should actually be 365. See, I just wrote a 5 there. Got too used to that. 24. So then times it by, so that's days, times it by hours. So let's actually see how different that value comes out. 365.24 times 24 times by 60 times by 60, and that comes out. I'm going to round this because it's come out with some decimal places. 557 should be our conversion factor. This is how many seconds are in a year. Let's go up and see how different it is. I'm going to recheck my calculation because those two numbers have come out differently, which is a bit strange. 365.24 times by 24 times by 60 times by 60. Aha. Yes, I don't know where I typed that in wrong before. Let's fix that because that doesn't seem right. 5065, 736 seconds. So you can see this comes out very close to this number. So it's still 31 million. The next is a 5. And see, you can see that's the last few numbers where it starts to deviate. So we've got 4 significant figures where they're accurate too, which is why we tend to just use 365 in there. But you can see there are slightly different values. All right, let's get on to the fourth and final section of this video. Use significant figures and standard form where appropriate. So we've seen standard form, but I want to get into it in a bit more detail. So first of all, let's just name some things. So this number down here, this I believe has the term mantissa. So in physics, this is always going to be a 10, but in maths you'll come across ones where it's not 10. Maybe when we're in radioactivity, we use 2 instead of 10, but most of the time it'll be 10. This number in here is called the exponent. So just to place some limits on them, so a mantissa has to be between 0 and 10 exclusive. So it's going to be so not between 0 and 10. Sorry, it needs to be between 1 and 10. So it's not going to be like 11, for example. It's not going to be 0.2, for example. An exponent is going to be an integer. So it can be negative, it can be 0, and it can be positive, but it has to be a whole round number. So some useful things to remember when we're dealing with powers of 10 is if the exponent is a positive number, we're going to be moving the number to the left, and I'll show you what that means in a second. If the exponent is negative, we're going to move the number to the right, and I'll show you with some examples what that actually means. So essentially, these are trying to tell us how we convert between decimals and standard form. So let's start off with some decimals to convert into standard form. So at the moment, this is 109,000, but the mantissa has to be between 1 and 10. So the mantissa here is going to be 1.09. So you can see I've just taken the numbers which aren't zeros like these ones at the end, and you can see I've expressed it as a number between 1 and 10. And so now what we need to do is count how many places to the left the 1 has moved here. So 1, 2, 3, 4, 5. So what we're going to do is write 10 to the power of 5. So this is our mantissa 1.09, and between the two, we've moved this 1, 2, 3, 4, 5 places, which is why the exponent is plus 5. So things like in the thousands, millions, billions, we're going to expect to see positive exponents. Let's do the same thing here. So the mantissa is going to be 6.7. It's got to be between 1 and 10. So here we have moved the 6, 1, 2, 3, 4, 5 places to the right. So the exponent here is minus 5. So when you've got decimals, we're going to see exponents which are negative. Let's try and do it the other way. So let's convert standard form into decimals. So what we're going to do is we're going to move this 1 6 places to the left. So there we go. So let's just see this. So the 1 was here in this units column, right? So we're going to move it 6 places. So 1, 2, 3, 4, 5, 6. So that's actually 1.2 million. in decimal form. Let's do one like this as well. So we're going to have, so this would be moving it one place, this would be moving it two places, and then we write our 5, 6. You can see the 5 was in the units column, right? And so we've moved it 1, 2, 3 places to the right here to account for the -3 in there. Okay, so what we're going to do now is I'm going to give you a couple to have a look at here. Let's not creep into the next section. So there's one number to convert into standard form, one to convert into a decimal. Pause the video and have a go at those now. Alright, so I'm going to assume you've done that. So with this one, the mantissa is going to be 1.3. So all of the rest of these are zeros, so we're not going to write those. And then we need to figure out how many places we've moved it. So 1, 2, 3, 4, 5, 6. And it's a really big number, so it's going to be a positive an exponent there. Let's do the opposite. So we've got a standard form here. So we're going to write, so that this would be moving it once, twice, 3 times, 4 times, 5 times, 6 times there. So you can see the 4 is in the units column here, so it's moved once, twice, 3 times, 4 times, 5 times, 6 times there for the -6 there. So it's been moved to the right 6 places. Okay, so the second part of this is dealing with significant figures, which really only becomes relevant when you're giving answers to calculations. Essentially, when you're writing an answer, you need to write it to an appropriate number of significant figures, because quite often your calculator will just give you loads of decimal places and things like that when you actually type numbers in. So some rules to remember, and then I'll show you some examples of them. Non-zero numbers, so 1, 2, 3, all of those things, are significant figures. So if you see them, that will count. Zeros to the left of the first non-zero number are not significant, and zeros to the right of the first non-zero number are significant, and that's reading left to right. Now that's a load of gibberish to start off with, so let's actually see that in action. Okay, so here is the first non-zero number reading from left to right. So this is what we're going to use. So these zeros are all to the left of that. So these are not significant figures. The 2 and the 5 are. So this is a 2 significant figure number. Okay. This here is the first non-zero number. So zeros to the right of it are significant. So this is a 4 significant figure number. Here, this is the first non-zero number. So that and that are not significant. So that's actually a 3 significant figure number. This is our first non-zero number. So those are not significant. That other 0 is, because it's to the right, that's a 3 significant figure number. Okay, so that's all well and good. We can recognize how many significant figures a number is. So why do we need to know that? Well, before we get into that, we're just going to do a quick assessment point. So pause the video, and all I want you to do is recognize how many significant figures are there in each of those 4 numbers. All right, so let's have a look. So here is our first non-zero number. So those 2 zeros are to the right of it, so those are significant. This is our first non-zero number. Those 2 zeros are not significant, so that's actually a 1 significant figure number. Here is our first non-zero number. That's not significant. There we go. And then here, last one, here is our first non-zero number. That's not significant. That's not significant. That other 0 is, because it's to the right. So that's a 365. 3 significant figure number there. Now, if you want a bit more practice of this, there's a really nice assignment on a website called Isaac Physics looking at significant figures. So if you want some more practice of that, that's a really good place to go find it. But let's finish off by seeing, well, why do we care how many significant figures a number is? Well, there is a rule that we are going to use during calculations that answers should not be given to more significant figures than the data used to calculate them. Okay, so that's why we need to know how many significant figures something is. The reason for this is you can't calculate something more precisely than the actual measurements that went into calculating it. That's kind of where that comes from. So if we look at this calculation here, this is a 3 significant figure number. This is a 2 significant figure number. So if we type that into our calculator, that's probably just going to come out as 3 on your calculator, but what we should actually be writing is 3.0. So I'm giving the answer as a 2 significant figure number because we are limited by this 2 significant figure number we are using in the calculation there. So the fact that this is 3 is not important here. We can't give more than this piece of data here. Let's do the same thing here. So we've got 30 times by 2.00. So that's basically 30 times by 2. So I'm going to give that answer as 60. Reason being, that's a 2 significant figure number. That's a 3 significant figure number. So I'm going to give my answer as a 2 significant figure number there, because we can't go more than this there. We just can't be more precise than 60 here, despite what our calculator may or may not say. Okay, so final one. Couple of questions for you to have a go at. Pause the video now and write your answer to these questions to an appropriate number of significant figures. Alright, so let's have a look. So first thing we need to do is analyse this. So this is a 3 significant figure number. This is actually a 4 significant figure number, because remember, zeros to the right of the first non-zero number are significant. And then if we actually type those into our calculator, so 300 times by 1.500, it's going to be like 450, I think. So I'm going to write that as 450. So I'm going to write that as a 3 significant figure number there. Because the fact this is 4 is not important, we're limited by this one here. And we've got 20 divided by 4, which is going to be like 5. So this is a 2 significant figure number. This is a 3 significant figure number. So I'm actually going to write it as 5.00. No, we're not. We're going to write it as 5.0. We're going to write it as a 2 significant figure number because we're limited by this number here, but it does allow us to be this precise. So we can be more precise than just saying 5 there. Okay, so that brings us to an end of the content in this video. So these were the specification points we were trying to learn in there, so these 4 here. I would highly recommend at a later point you have another go at these assessment questions, because that's the only way you're going to find out if the stuff is actually stuck in your head by reattempting these little quizzes in here. So it might be worth saving this document somewhere or printing out another copy for later on and check that you've actually learned these things as part of the process. But that's where we leave off this video, and we'll pick up with the next one where I think we'll be looking at forces.